Our first question comes from Sibusiso Sibanda. Sibusiso, thank you for this question. It is a geometry question, and I'm going to show you how to approach your geometry, folks. I've always, when I teach geometry to learners, they try and save this diagram. I don't know if they want to save it for their grandchildren one day so that they can do the geometry, but that's not how we do geometry. The diagram is the key to everything that we're going to ask you in a geometric question. So you're going to read that little top paragraph. You're going to fill in that information in signs and symbols and colors on the diagram, and you should spend at least 5 minutes on coloring in your roadmap. I call this diagram the roadmap. Let's see how we go about this. Okay, our first bit of information says that ABC is a tangent to the circle at B. I stop reading immediately. Now I use that information and I fill in everything that relates to that tangent on this diagram. Now let's remind yourselves. There's the Chord Theorem. The Chord Theorem says the angle or the line, the angle formed between the tangent and the chord is equal to the angle in the alternate segment. So that's the one. The second one is if there are two tangents running to the same circle, those tangents are equal in length. Your third tangent theorem tells you that if you have a tangent and if you have a radius or a diameter, those two things are perpendicular. Now let's see, what do we have? We have the tangent ABC. We've got a chord at FB. Okay, so let's stick to that for now. The angle between the tangent and the chord is lying in this segment of the circle, is equal to the angle in the alternate segment. So it's equal to the angle over here, E1. So we can say that this is an X. Okay, there's another chord. There's a chord at BE. Now at BE, the angle between the tangent and that chord is this big angle. Let me use yellow here. Yellow doesn't look as nice on the white. Let's take it to a blue color. So the angle between the tangent and the chord is equal to the angle in the alternate segment. Now that is just by using the fact that this is a tangent, it touches at B. In this diagram, there's absolutely no radius given and there's no diameter given. There's also not another tangent that's drawn to the circle. So we're happy with what we've got so far. Let's read on. They say to us, from point C, this is the point down here, a line is drawn parallel to BF. Now there's BF. Okay, let me try and find my highlighter here. I hope I'm going to find my highlighter. There we go. So BF is parallel to DC. Okay, so we've indicated that so that we do not forget what it is that we're working with, folks. Okay, so we select our pen again. If those two are parallel, let's see what else can we now do. I just want to get to my pen and I want to get to the particular color that I'm looking for. There we go. I'm looking for the green. Okay, so this line is parallel to that line. Folks, now you can see here that AC is a transversal. So this whole angle here at C, C1 and C2, is also an X. Why is that the case? Well, the angles are correspondingly equal to each other. Those lines are parallel and we have a transversal. We can also say more now. If we look at the angle here at E1, the angle at E1 is equal to the angle here at X, which is then equal to the angle C1, C2. So those three angles are indeed equal to one another. Okay, folks, so let us see what else we can do with what we've got here. Here at the top, at F, we've got that angle. Okay, the angle here at F at the top. Can we say anything about any other angle? Remember, these are indeed parallel to each other. So the only thing we can say is the angle at F and these two angles here at D are supplementary. They're co-interior angles. Okay, so I think for now we are happy with what we've got. Okay, let's just see one last one here. We have this line, BD. Now BD is a transversal that runs across from B to D, the parallel lines. So this angle here at D, I'm going to make it a little orange angle for now with two lines, is equal to the orange angle down here. Those are indeed, are they? They are not equal. They're not equal. We're at the wrong angle here. It's angle D2. So let me just get my orange back. It's angle D2. That is indeed equal to angle B2 and angle B3 together. Okay, so that's your Z that you have from your alternate angles that are equal. Okay, let's read on. So we had that they parallel and that they meet one another at the point D. EC and BD are drawn, so that just tells you EC is a line segment and BD is a line segment. So those two are straight lines. Then E1 is equal to E2 is equal to X. Now that they gave us on our diagram, so we can say this one is also an X. So we've got those four X's. C2, this angle down here, let me make it a dot for now and let's make it a blue dot. The angle here at C2 is equal to Y. Okay, I think we've got everything from that little paragraph translated into symbols on our diagram. Okay, don't forget the parallel lines. They might be key in some proof. Let's see what they ask us. The first question says, give a reason why B1 is equal to X. Why the following is true. Why was B1 over here equal to X? Well, it was equal to E1, tan chord theorem, and E1 was equal to X. So B1 is equal to X was equal to E1. And the reason for that would be tan chord theorem for 1 mark. Okay, so that's quite nice. BCD. BCD, the angle down here, they ask us to show that it's equal to B, or why is it equal to B1? Well, we said that from the beginning. Here's our parallel lines. There's our transversal cutting the two parallel lines, so those are corresponding angles. So our reason, corresponding angles are equal. Why? The line FB is parallel to CD for 1 mark. So far we've got 2 marks. Okay, now for 2 marks. They ask us, prove that BCDE. Now let me color in B, C, D, E. Prove that that is indeed a cyclic quadrilateral. Okay, now we've got to think. We do not have it as obvious on the diagram, so there's something that we might not have seen. Let's dig a little bit deeper. To prove, excuse me, to prove this is a cyclic quad, we can prove that angles in the same segment are equal. In other words, E2 is equal to D2, or any of the others. Or we can prove that the exterior angle equals the interior opposite angle, which is the case here if we look at E and C1 and C2. This angle here is X. That angle here at E1 is an exterior angle. So it's easy. It's very, very easy. Let's do it on the side here. we're going to argue that E1 is equal to x, which is equal to, now remember, B1. That was the tan-chord theorem. Okay, we've already had that BCD is equal to B1. So angle C1 plus C2 is equal to B1 over here. Okay, so this will be equal to then C1 plus C2. So we've argued that E1 is equal to C1 plus C2. And this here was proven earlier, or we've used it in 9.2. So therefore, the figure is indeed EDCB is indeed a cyclic quad. The reason is the exterior angle is equal to the opposite interior angle of that quadrilateral. Now folks, that means a lot. Let me draw the cyclic quad in. I'm going to draw it in blue so that it stands out for us. Now you might want to use highlighters in your exam papers to draw this. There's our cyclic quad. Now we've got a lot of other theorems that apply to that quadrilateral. That quadrilateral is concyclic. So we've got angles in the same segment that are equal. We might have other exterior angles that are equal to each other. We've got opposites that are supplementary. Let's have a look. D2 over here is equal to E2. So these orange double lines are in fact green lines because of the fact that BC subtends. So that's an X, another X, and this here will then inevitably also be an X. So B2 plus B3 is also X. Okay, why is that the case? Because these two angles were equal to each other. They were alternate angles. Okay, so then we can also say, now let us just bring all the angles that are equal to each other. I'm going to bring a black line in at B4 is equal to the angle at E3 because the chord DC subtends it. Then let's put a little, what can we do here? Let's put a star in this one is equal to D1 up there. And then this blue dot was equal then to the black dot over there. Now, why is that the case? Let me just remove that black dot that I put in there by X1 so we don't confuse ourselves. Okay, why was that the case then? Because the angle for all of these, the angles in the same segment became equal. Okay, but there's one more angle that we did not pay attention to. Look at this. This big angle over here, there, is the exterior angle to the cyclic quad, which is equal to the interior opposite, which is that full angle up there. Okay, so we can see, folks, our roadmap is full of information. Let's see what the next question asks us. If we did our job properly, the answer should be on that diagram. Let's have a look. We've proved it's a cyclic quad. Which two other angles are equal to x? They want two other angles that are equal to x. Let's do this up here. Well, we saw that D2 became x, and that was because of angles in the same segment that are equal. Okay, so D2 became an x here. That was an x, so D2 was equal to E2 it was, and E2 was in any case equal to x. So D2 is x as well. And because D2 is x, we can say B2 plus B3 is x. So also B2 plus B3. Where's B2 plus B3? That angle over there is equal to x. And why was that so? It was alternate angles that were equal, and obviously the lines that are parallel again, FB and DC. FB is parallel to DC. Now let's go down for our next one. For 3 marks, we got to prove that B2 is equal to C1. Now let's see if that is indeed already the case. B2 lies over here. Let me put, what can I put in there? Let's just put a little orange circle around B2. We want B2 equal to C1. And C1 is this angle that lies over there. Now, folks, you can see if you look very carefully, look carefully at what we've got. We've got B2 plus B3, this whole angle here, is equal to C1 plus C2 over there. But B3 is equal to C2, angles in same segment. Therefore, C1 must equal B2. So let's write that out quite nicely. Okay, I'm going to use the color green here. So for the last one over here, we're going to argue that B2 plus B3, B2 plus B3 is equal to C1 plus C2. Remember, they were both equal to X. We've proved that before. So that's proven that those two angles are equal to each other. And we can say now, let's make a tad bit of space there, and B3, the angle with a black dot there, is equal to C2. And B3 is equal to C2. And the reason, angles in the same segment are equal. Okay, so if B3 is equal to C2, and collectively those are equal, we can then conclude that B2 is therefore equal to C1.